Welcome to classes by Inspire Physics. Today we have a problem in electromagnetic induction. So I'll read the problem. In the given figure, the arm PQ of the rectangular conductor is moved from x is equal to 0 outwards. The uniform magnetic field is perpendicular to the plane and extend from x is equal to 0 to x equal to b and is 0 for x greater than b. Only the arm PQ possesses substantial resistance small r. Consider a situation where the arm PQ is pulled outwards from x is equal to 0 to x equal to 2b and is then moved back from 0 moved back to x is equal to 0 with a constant speed b. Obtain expressions for flux, the induced EMF, the force necessary to pull the arm, and power dissipated as joule heat. Sketch the variation of these quantities with a distance. So we have the situation here. This is the magnetic field region. Actually in the diagram it is shown like this, but from x is equal to 0 position to x is equal to b, we have magnetic field. We need not consider the magnetic field in this region. Okay, I'm not considering the magnetic field in this region. From here to here we have magnetic field. We have a rectangular frame and this side you can see it is movable like this. Initially it was here. We just start moving like this. So when we move in this direction, what happens? In the rectangular region, the area of the rectangular region increases and the flux also going on increasing. Okay, so from the position from K to L, what increases? The flux linked in the rectangular loop increases. How will you get equation of flux? We know flux is equal to phi is equal to B into A, B into L is the length of the conductor small l, X is the distance. So from 0 to B, this is the position B, that is K to L, we have a flux increasing like this. When the position X increases, flux increases. So X is an increasing quantity. X increases. Now at this point, when the conductor reaches here, this is the maximum distance x is equal to b, the limit of this magnetic field region. Distance is x is equal to b. So that's a maximum flux. Thereafter no flux here. So maximum flux equal to BL. Instead of x, what we will give? We will give the position B. BL, that's the maximum flux. Thereafter, when we move in this direction, there is no flux. So from B to 2B, the magnetic flux will be the constant. That is, constant value means it is BLB. Thereafter, no change in BLB. BLB remains constant. Okay, so from B to 2B, we have the flux value constant flux. Now we need to plot a graph with the flux with the distance. See, if, we know that from K to L, the flux is given by, that is 0 to B flux given by BLX. X increases. Since x increases, when you plot a graph, we will get an increasing graph up to the point L. At the point L, we have the maximum flux. What's the maximum flux? It is BLB. Thereafter, the flux remains for this movement from L to M. Means this is called outward movement. In the outward movement from L to M, the flux is remaining at a constant value. Means this flux remains constant. Thereafter, no change in, no increase in flux because there is no field line in this region. From x is equal to b to x is equal to 2b, or from L to M, there is no magnetic flux. So what we can say, the magnetic flux remains constant. This is for outward movement. For the returning movement, that is inward movement, then also from M to L, the flux remains at a constant value. Okay, because the flux remains at the maximum value. What is the maximum value? BLB. So in this region, we have flux constant. In this movement also, the flux will be constant. Thereafter, what happens? When we move in the backward direction, the flux going on decreasing. We can see the flux is going on decreasing. Forward, we can say flux is BLX. Then backward, we can say flux is minus BLX. If you want, we can give. It is decreasing like this. To indicate that, we can put a minus BLX for the movement from L to K. Okay. So from K to L, we have flux BLX. L to K, we can take the flux will be minus BLX. Now we need to plot the induced EMF. We know induced EMF is minus d phi by dt. For the movement from K to L, there is increase in flux. Okay, what is EMF induced? Minus d phi by dt minus d by dt of BLX. BLX is the flux. Okay. So what will be the induced EMF then? BLX. It is dx by dt. What is dx by dt? It is velocity. So BLB. BLB is a constant value. BL, velocity is constant because constant speed. We can say induced EMF from where to where? K to L is a constant value. So from K to L, induced EMF is a constant value. This is the constant value minus BLB. Then what happens from L to M? L to M, what happens is when you move from L to M, see we find d by dt, induced EMF BLB from B to 2B, that is L to M. The flux is having a constant value. BLB is a constant. When you differentiate the constant, we will get a 0. From L to M, we have EMF 0. Return journey M to L, then also EMF will be 0 because no flux changing here. Now coming back L to K, the flux going on decreasing. Okay, increasing flux we have given BLX, that is from K to L. From returning, we can say L to K, it is decreasing. Or for what we can say from K to L, so L to K, we can say for L to K, the flux we can take a value that is minus BLX. Okay, minus BLX, this is indicated here, decreasing. Then what will be the EMF induced? E is equal to minus d by dt of what we will say, it is minus BLX. When you differentiate as we have done here, we will get EMF plus BLB. Plus BLB. So for the return journey, means inward journey from L to K, what is induced EMF? It is a positive value plus BLB. So induced EMF is a positive value plus BLB. Okay, so EMF is plus BLB for the journey from L to K. K to L, flux increases. Okay, we have got EMF negative value. L to K, flux decreases. Decreasing flux we have indicated by a symbol minus BLX. Then EMF will be plus BLB. These are the values of induced EMF and flux at three different regions: K to L, L to M, M to L, and L to K. We have plotted a graph of flux as well as the induced EMF. Now we need to plot a graph for power, force and power. Okay. Now first we see current. See, we know that induced EMF is minus BLV from K to L. That is 0 to B. This is induced EMF minus BLV. Then what is induced current? Current is EMF by resistance minus BLV by R is the induced current. If induced current is there, what is the force experienced? Force equal to BIL. B into I into L. What will you get? Minus B square L square V by R is the force experience in the region from 0 to B. So from 0 to B, that is from K to L, once outward journey, the force experience is negative value, constant negative value minus B square L square V by R. Thereafter from L to M induced EMF is 0. So force also will be 0. Force will be 0. Returning also from M to L, inward journey. Then also L to M induced EMF is 0. Then force will be 0. So L to M and M to L we have force value 0. Now L to K, what happens? L to K we need to find the force. See, L to K we have induced EMF having a value of BLV. If it is BLV, what is current? Plus BLV by R. Here we had a minus BLV by here we have plus BLV by R. This is current. Then what is power? Power is equal to I square R. Okay. Sorry, we have the force. Force is equal to B square L square V by R. Okay, we have the positive value of force. Here we had a negative value. From L to M we have positive value of force because force equal to BIL, but I is equal to positive value from L to K. Means I is positive value, F is a positive value. Same value will be there, but it is positive. We have positive constant value. Now we need to find a power. How will you find a power? We have power is equal to, we have the equation I square R is the general equation of power. We know that power P is equal to, equation is I square R. Okay, I square R. Now K to L. K to L we need to find I square R. K to L, what is I? I is a negative value. When you take the square to find the power, I square R, when you take the square it will be positive value. Then B square L square V square by R is the square of current with into resistance will be B square L square V square by R from K to L. Now L to M and M to L. L to M and M to L. There is no need of power because during this region force was 0. When force is 0, the power means current is 0. At these two regions, induced current is 0. Here also induced current is 0. Then power also will be 0. Now coming back to L to K. When we come back to L to K, current is positive value. This was negative value, now current is positive value. Again, when you find a power, square of current, a positive value of power, b square l square v square by, we will get a positive value of power. So power is positive in both cases because we take current. Power is I square R. Here negative current because EMF was negative. Here positive current because EMF was positive. But in both cases, when you take square of the current, it leads to a positive value of power. Okay, so these are the values of power, force experience, induced EMF and flux. When we move a conductor in this region from x is equal 0 to b, k to l, we have magnetic field, L to M no magnetic field, M to L no magnetic field, L to K again magnetic field. In this moment, magnetic flux increases, backward moment magnetic flux decreases. Magnetic flux increases to maximum value, remains a constant value. Now also magnetic flux remains a constant value. Now also remains at the constant value. Now going on decreasing. So that's why we have got a first graph like this. First graph we have seen that the magnetic flux was increasing. Okay. Then becoming constant value then decreasing. Correspondingly, we have got EMF also. Negative EMF and this is positive EMF. Then based on the EMF and current values, what we have plotted? We have plotted the force experience as well as the power. Force equal to BIL using the value current. EMF by resistance is current. We have got the current and we have calculated force. So force for move forward journey and for backward journey. In these two cases, there is no need of force because EMF was 0 at these two regions. L to M and M to L EMF was 0. There was no force. Okay. So we have done the graphs, plotted graph for power, force, induced EMF and flux. Okay. It's a very important problem in electromagnetic induction and hope that you have understood. Okay. Thank you.